If this is the Earth, and we have a point mass on the surface of the Earth of little m, what is the gravitational attraction between this point mass and Earth? According to what we learned, that a spherical symmetric distribution, that we can assume the total mass is concentrated at a geometric center. So we can assume that the mass of the Earth is concentrated at this point, which is one radius of the Earth away from the point mass of little m. Since we have 2 point masses now, the gravitational force between these two can be written as f of g equals to time constant, mass of the little one, mass of the Earth, production, divided by their separation squared. That is RE of square. Now what if we have a tunnel through the Earth? That little m actually gets into this tunnel, and which is a certain distance away from the center of the Earth, but it is less than the radius of the Earth. Let's decide this one be a little r. Right now the little r is less than the radius of the Earth. What is the gravitational attraction now between the Earth and this point mass m? Let's name it m prime. Well, this is a little bit strange situation. Let's take a look what happens. As a matter of fact, if we look at this line, all the mass above this line will attract m prime upward. So the net force is up. And all the mass underneath this line will attract this m prime downward. Well, we have more mass underneath this line, but further away. And we have less mass on the top of it, but it's closer to the m prime. As a matter of fact, we can use calculus to prove that actually the net force from the top and the bottom eventually comes down to such a situation that if we redraw this Earth, and this is the radius of the Earth. Now if this m prime located here, we can simply use the little r to draw a core. And as a matter of fact, the net force attract m prime will come from this core. So for the little m prime, that core behave like a little Earth. So m prime is outside of this core, and the mass of the core we can still consider concentrated at the center. Now since this is a symmetrical distribution, so we can find the mass of this core. Let's name ME of prime because this is a new one. It should be per volume. So if I use ME prime divided by the mass of the Earth itself, and it should proportional to the volume because density is the same. Therefore, we can have volume is 4/3 pi r cubed. So actually is this little r over RE, that ratio of cube. We can find the mass of the core, ME prime. Therefore, the force between the M prime and this core can be easily written as that FE prime equals to that capital G, this little mass M prime, MME of prime, divided by, right now this is outside of the core, and the radius of the core is R, so we still treat the situation as the first one because M prime is outside this core, so the gravitational force actually has come from this core. The outer layer, the force cancels out. Okay, so if we plug in what we have for ME prime, ME primes come from here, that is little r over RE of cube times mass of the Earth and divided by r squared. And we get a very interesting situation. Let's take a look. Constant, m prime is the mass of this point, and me is total mass of the Earth, and re is the radius of the Earth. So we have little r cubed divided by r squared. So it is a group of constant that is capital G m prime of me divided by re of, that's a cube, n times r. We get a situation that gravitational force from the core to the m prime is proportional to the radius. This reminds us a simple harmonic motion situation, because right now that the gravitational force is pointing to the center of this core. So this is a kind of like restoring force, because if I draw this picture clearly again, this is the direction of the radius direction, and m prime right now is right here, and the force Fe of prime is pointing to the center. That is kind of a restoring force, and this force is proportional to the displacement, because right now m prime is little r away from that equilibrium position. So according to what we learned, F equals to ma, what we have is, this is restoring force. That's why it's negative, because it's opposite direction of the r direction. Negative g m prime me over re cubed, and r equals to ma. Right now, since the motion will be linear, that a will be dr dt of second derivative. So if we define this is a constant, and let's take a look. If we define this as constant k, and move this negative term to the left side, what we have is dr dt second derivative, and we divide by m, and both sides of the equation, we will have plus k over m of r equal to 0. This is a simple harmonic motion equation, because that we learned from the previous chapter. So it is very interesting that the particle m prime, as a matter of fact, will perform a simple harmonic motion. Why is that? Because at this position, the force is pointing to the equilibrium position. So m prime will start to accelerate. So the speed will actually increase. Right at the center, since r equal to 0, when r equal to 0, force equal to 0, which means no more force. No more force only means no more acceleration. But this m prime accelerated, well, acceleration magnitude is not a constant, but acceleration is there. So the speed just gradually increase. So at this location, speed is the maximum. That's why m prime cannot stop or continue to go to the other direction. And let's take a look at it, this situation. If m prime goes to the other direction, now the speed is this way. However, now the attraction force will go up, will point to the center of the core. So that force will behave as a deceleration force. So that's why m prime will slow down, slow down, slow down until reached final speed 0. And this force is still there. Therefore, m prime will start to accelerate towards this direction. So this is just like a spring system situation, that when a mass passes the equilibrium point to the other side, spring get compressed, so spring will resist this mass, and mass will slow down. But eventually, when the mass reaches the far left end, and the spring will push it back, so it will start to oscillate back and forth. And we can find the period oscillation from the constant here, because according to what we learned from simple harmonic motion, that omega squared equals to k over m, and omega defined as 2 pi f, and 1 over f is t, that is the period. So as a matter of fact, if we know all the constant here, and as a matter of fact, we can find the omega. If we find omega, we find a frequency. That frequency is the frequency of oscillation, then we can find the period. It is roughly around 84 minutes for a round trip. Okay, let's look at another problem. This is a ring. of mass uniformly distributed. This ring has mass of, let's have capital M, radius r. Therefore, the linear density of this ring can be calculated by that mu equals to mass divided by the circumference, which is 2 pi of r. Now, there is a point mass of little m. How far away from the center of the ring? Well, first of all, x-axis is perpendicular to the plane of the ring. And so that's why this is a 90 degrees angle. And how far away is this? Well, let's assume this is a distance of a away from the center of the ring. The question is, what is the gravitational attraction between the ring and this point mass m? Now, probably you will think, well, this is a ring and this is a symmetrical object. But don't forget, this is not a symmetrical spherical object. Only the symmetrical spherical distribution that you can consider the mass concentrated at the center and then treat as a point mass to calculate gravitational attraction with as a point. And now this is a ring. It's not spherical. So what we can do is we still have to use Newton's law of universal gravitation. That is F of g equals to capital G, a point mass m1 times a point mass m2 divided by their separation square. And we have to start from there. So let's cut a piece named dm. That is a very small piece. That is a point mass. Now, this dm is point mass and this little m is also point mass. So they're going to attract each other. How? The attraction is on the line of their connection. So if we consider the attraction that dm give to m, then that force is this way. Let's name df, tiny little force. Let's name dfg, it's gravitational attraction force. Now if we cut a piece on the top, we can always find a symmetric piece, that of dm underneath. And so therefore you can imagine if we connect that, there is a similar dfg that this piece of dm gives to that point mass m. Since this is a symmetric situation, then the dfg on the top, the magnitude, equals to dfg underneath. So as a matter of fact, if we look at the situation, we have a d of fg this way. This is the x-axis, and this is the angle of alpha, let's say. And then we have another dfg of same magnitude and same angle with respect to x-axis. This is the x-axis. The net force of these two will be at opposite direction of x-axis, point to the center of the ring. So actually it is the dfg of cosine alpha survives. The dfg sine alpha, this component cancels with the other dfg sine alpha. So the resultant of these two is twice of the dfg cosine. This tells us, as a matter of fact, if I cut another piece of somewhere else, let's say here, and you can find a symmetric point there, all the resulting pair will eventually point to the center of the ring, and all time cosine alpha. So the net force between the ring and this point mass m, f of g, as a matter of fact, is the summation of the all dfg times this cosine of alpha. Now, this cosine alpha can be written as side adjacent, which is a, it's a constant, divided by the hypotenuse, which is, this is the radius of the ring. So that should be r of square plus a of square and square root. A square, r square, square root give us this. So cosine alpha is this, and it's a constant. So how do we find the total fg? Now we have to express dfg. DFG, it is a force between 2 point masses. One is the dm, the other is the m. Okay, so we have this capital G, point mass m, and dm divided by their separation square, which is r squared plus of a squared. So if we plug in this expression dfg into here, what we have is, as a matter of fact, g, m, and this is all constant. So as a matter of fact, we will have this capital G, m as constant, and cosine alpha as that. So we have a, and denominator we have r squared plus a squared of 3 to the 2 and dm. So it is very interesting. The summation, which is integral, comes down to adding all the dm. You add all the dm on the ring, that's the total mass of the ring, capital M. So the result is G, little m, capital M, over, I'm going to write this, of r squared plus a squared, and a divided by r squared plus a squared square root. Why I'm doing this? Because I want you to take a look at the dimension. Here we calculate gravitational force Fg. According to Newton's law of universal gravitation, no matter what happens, the units should be capital G, kilogram square and meter square. So capital G, this kilogram square, this is a meter square. So this is the force in Newton. And here obviously is dimensionless because meter square plus meter square, that's meter square square root, that's meter, meter, meter cancels. As a matter of fact, this is a cosine alpha. That is dimensionless. So let's take a look at one more time. If we mistakenly assume the mass of the ring is concentrated here, and this is mass of the ring, if we assume, and then that little m is a meters away. If we treat this way, then the gravitational attraction between the ring and m will be, first of all, direction will still same, but the expression will be Fg equals to capital G, mass of the ring, mass of this guy, divided by a squared. As is totally different compared to what we learned, what we did integral from here. So again, I want to point out, this is wrong. You cannot assume mass of the ring concentrated here to attract the other one. Well, obviously, if you talk about center of mass, yes, center of mass, you can assume mass of the ring. Right now, we're doing gravitational attraction. Remember, only the spherical symmetric distribution. You can assume the gravitational attraction mass concentrated at a geometric center. The ring is not a spherical symmetric distribution. So you have to cut a slice of the m and to find out what is the attraction between this point mass and that point mass, and that is our df situation. Eventually we figured out we have to add all the x component of the gravitational attraction and we'll get the net force.